Alrighty, welcome back to operating systems. Light today, eh? So, what's going on today? Alright, well, this is the last lecture of actual content. Past that, next one will be virtual machines and then just review sessions. So, this one is valid for the final. I forget, I wrote it a while ago, so I forget if there's a question on it, but yeah, this is the last lecture that is actually covered for the final, and guess what, the final's next week. So that's fun. All right, so we left off last lecture talking about how the kernel would allocate memory, and it wouldn't just use a free list of any old size, it would do something different, and today is that different thing, and it kind of relates a bit to Lab 6. So, the allocators that the kernel uses are called buddy and slab allocators. Why would it be called the buddy allocator? Well, because it uses the idea that memory can be buddies with another piece of memory. So how it actually works is it restricts the problem a little bit. So in the general case, we have to deal with allocations of any size, and we make our blocks the same size as the request. But the buddy allocator does not do that. The buddy allocator restricts it a bit and only does allocations internally, at least in powers of 2. So every allocation that it deals with internally will be something 2 to the n. So like 2, 4, 8, 16, 32, maybe 128. That's like an inode, all the way up to page size. Maybe it's more than that and manages a bunch of memory. So why it restricts powers of 2 is to have a more efficient implementation, and the idea behind it is it will just split blocks in 2, and you know that they are contiguous because one block is a buddy with another block they came from the same parent. So if you need to merge them back together, merging is really, really quick because you can check, because everything's aligned, check if you and your buddy are free. If you and your buddy are free, you can merge them back into the next power up power of 2. And with this, with most memory allocators, once you start implementing it, the problem becomes searching to find a free block of the right size, and merging is also difficult if you implement the just most general strategy. So, because we restricted it to be powers of 2 only, your implementation for buddy allocator can use multiple lists. So, since we restrict all of the allocations to be to the k, where that k could be 0 all the way up to n, and we round up if needed to a power of 2 if someone requests a weird size. So how the implementation would work is you have a free list for every power of 2. So there's a free list that just keeps track of all the free blocks that are size 2, a separate free list that keeps track of all of them of size 4, a separate one that size 8, so on and so forth. So if I went up to, n powers of 2, well, then I need n free lists. So how this works is if you get a request for size to the k, so say it's like 32 bytes or something like that, so you search the free list till you find a block big enough. So you search the free list for exactly 32. If that is empty, then you search for the next size up, so 64. And if there's no free blocks there, then you search up for the next power of 2 up, which would be 128 or whatever it was, until you actually find one. If you do find one, you just keep breaking them apart, keep splitting them in 2 until you create a block that is the same size of the request. And when you break them apart into 2, you create a lot of buddies. So you would create more entries for every power of 2 you had to create. You would add it to the free list. And for deallocations, what you do is that coalescing. So if you free an allocation and its buddy is also free, you coalesce or you merge them together to create a bigger free block. And you could do this recursively if you needed to create, the maximum size free block. So how would that look graphically? So say I have a buddy allocator and it is managing 256 bytes of memory. So anything with the dark background there or the filled in background, that means this block has been split into 2 and I'm not actually using it for allocations. So in total, I am managing 256 bytes, and I split that into 2 entries of 128. And then for each of the 128 byte entries, well, I split them each into two 64 byte entries. And for this 64 byte entry, I split it into two 32 byte entries. So this entry and its buddy. So anything that has a colored background means that it is used for an allocation. So there's a red allocation for 32 bytes, and then there would be a free block of size 32 bytes. So that would be stored in its own linked list that keeps track of all of the free blocks of size 32. For the 64 byte ones, well, there's two entries here, so there would be two entries in the free list. One's as good as any other one if you have to search for it, so it doesn't really matter. And then I have this blue or teal or cyan, I guess it's not really cyan, blue or teal allocation of size 64 bytes. So what would happen to the buddy allocator if a request comes in for 28 bytes? How would this, what would it do? Yep. Yeah, so check the list of 32 size. So 28 is not a power of 2. Got to round up to the next highest power of 2, which is 32. It would check the 32 byte free list. Hey, there's a 32 byte one. So it would use that and just do the allocation right there. So we would fill in the green allocation, and we'd have some internal fragmentation, right? We'd have 4 bytes of internal fragmentation because, well, we're only using 28 bytes of that 32 byte block. So what happens now if we get a new request for a 32 byte block of memory? Yeah. Yep. Yeah. So we would search for exactly 32. Right now there are no free 32 entries, so we go to the next power of 2 up. Search for 64. This one doesn't really matter what you pick. One as good as any other. So we would take this 64 byte block, split it into two 32, and then we would use a 32 for the allocation and then put another 32 back onto the free list. So it should look like this. So now we have our purple allocation, and we have one 32 byte block free and one 64 byte free. So what's going to happen now if I free that 64 byte block? So this one becomes free. Is its buddy also free? Yeah, so its buddy is also free, the one that was allocated beside it. They both have the same parent. So we could create an even bigger free block. So we could create a 128 byte free block out of those two. And we can't go the next level up because, well, we're using the other buddy. So at the end of the day, we would be left with this after all the allocations. So any questions about that? That is the buddy allocator in a nutshell. All right. Probably be quick today. So yeah, the buddy allocator, that is one of the primary allocators that are actually used internally by the Linux kernel. Advantages, well, it's fast and simple compared to just general dynamic memory allocation where we just have a free list and we have to search it every single time when there's just one free list. And coalescing is really hard. Searching it is really slow. So this is a much better approach for that. The only disadvantage is that we have powers of 2 and we can only do that. It also kind of avoids external fragmentation because it keeps things contiguous because, well, it only has, you have buddies, so it's a lot easier to keep addresses contiguous if you're doing that approach. You can get into the same case where you do have fragmentation, but it's at least a lot better with the buddy algorithm. The disadvantages is with this, if you don't have powers of 2 allocation, there's going to be some internal fragmentation you just can't handle because, well, you only deal with powers of 2 internally because you always round up. So the last one, which is kind of related to Lab 6. So this lecture is built to be really short, so I will be here, and I suggest you work on Lab 6 if you haven't done it already, and I will be here for any questions. So the last option is a slab allocator, and that further restricts it. So for a slab allocator, all your allocations are all the same size. So how that works is you just allocate essentially a giant array, giant pool of objects, and since everything is of the same type and of the same size, well then one is as good as any other, and you can just keep track of whether it's allocated or not by just having essentially a giant array of bits that will keep track of each slot. It will be 0 if it's unallocated and 1 if it's allocated or used. So this wouldn't have any internal fragmentation because you assume that everything is of the same size, so you don't have any of the fragmentation issues. One slot is as good as any other slot. So you will find this with Lab 6 because you essentially have a giant array of inodes, and then your inode bitmap keeps track of what inodes you are actually using. So it is actually an example of a slab allocator for your file system. So you can think of the slab as just a cache of slots or elements in an array if you want. So each allocation has a corresponding slab, like a slot or an index, however you want to think of it. And one slot is just one element of the array. It's one allocation. So instead of having a linked list, we're essentially just using arrays, and that's what a bitmap is. So there's just a bitmap. So for each slot, you just have one bit. Keep track if it's allocated or it's not. And if it's trying to allocate memory generally, or allocate one of the elements of the array, for allocations, it's really quick. All you do is search the bitmap until you find some byte that has a 0 in it. If you find one that has a 0 in it, that means that slot is free. You can go ahead, use that slot, and then you just flip the bit from a 0 to a 1 to indicate you are now using that slot. And then for deallocations, it's also super fast. You just figure out what bit you need to change from a 1 to a 0 to indicate that it is now free. And then you may or may not actually clear the memory for that and set it all to 0. Typically, computers will not do that, and kernels won't do that because it's slow to do that. It's faster just to mark it as unused, because next time you use it, you'll probably just overwrite the data anyways. So what's the point of wasting time setting it all to 0? And the slab, well, it can be allocated on top of a buddy allocator, on top of any general one. So typically, if you really care about performance and you are creating thousands and thousands of objects of all the same type, typically what people will do for performance is essentially create a slab allocator, just ask malloc for a bunch of memory, and then implement a slab on top of that, and just have a bunch of, just treat it as a giant array where they just keep track if a slot's allocated or not. So it could be on top of a buddy allocator, it could be on top of malloc. Typically, when you implement this, sometimes it's called an arena. Sometimes people will call it an arena if they're implementing their own memory allocators. But once you start caring about performance, you will probably implement something like this or use something like this. So if I have like two object sizes, A and B, what I might do is, well, I get slab 1 or A1 from the buddy allocator, and I might put like 4 objects of type A there, and then I ran out, so I need to ask the buddy allocator for more memory. So maybe I get this block and I call it slab A2, and I put 4 more A's on that, and I'm wasting some space within the memory I got from the buddy allocator. So say each of these, like I got, I don't know, 128 bytes from the buddy allocator, and each of these is some weird number like 30 bytes or something like that, 28, some number that doesn't quite fit. Then maybe I have bigger objects of size B that fit exactly within a block. So this one holds 2 B objects in B1. This slab for B2 also holds 2 objects. So in this case, well, you might notice that instead of having slab A1 and A2, I could have just used that entire space of memory and just have one giant slab of A objects. and maybe I could have reduced my internal fragmentation. Instead of fitting in 8 elements there, I could have fit in 9. So you might want to do something like that as well if your sizes don't match up, but typically you probably wouldn't want to do that because that's, again, moving memory, so you might make some addresses invalid and need to make sure that you update all the addresses and use all the newly updated addresses, which we already have enough memory problems. And if you're doing that in a multi-threaded application, well, guess what? Then you have to think about data races and all the fun stuff we know and love. So, any questions about these memory allocators stuff? Yep.
So in this case, like Slab, A1, A2, they have internal fragmentation.
Yep.
And could you also say like the blocks within A and A2, like they're kind of externally fragmented? So like there's smaller blocks there, I guess, like the red blocks in A1.
Yeah, so it's a bit weird. So typically you have talk about external fragmentation probably from the buddy allocator that allocated these slabs. And for that, it wouldn't have any external fragmentation because it only deals with powers of 2 and it just has internal fragmentation. So that's probably what you would consider in this case. All right, so rewinding to lecture 28, we ran out of time for this slide, so now we have ample time. So we can talk about journaling file systems. So remember back when we were trying to delete files, there wasn't actually a delete. It was just RM is just an unlink, so it just gets rid of the name to the inode association. So if you run out of, if there are no more hard links to an inode, then you can actually delete it. If you start doing lab 6, you will see the steps. In order for the kernel to actually delete and get rid of a file, there would be a 3-step process. So it would have to remove the last directory entry, so that gets rid of the name to the inode, in which case no one's using this inode anymore. So as the second step, you can essentially free this inode back to the pool of free inodes, so that would require changing the bitmap that keeps track of whether an inode's allocated or not. So in this case, it would change that inode from a 1 to a 0 since it's not being used anymore. And then we would also need to free any of the disk blocks that that file uses because, well, we're not using it anymore. So if it used, physical block 6, 8, and 10, for instance, we would have to set those as freed as well. But because this is all on a disk that is persistent, well, all of these operations, I could yank out the power cord at any time, assuming it was a desktop, or I could lose power or run out of battery or something like that. So between step 1 and 2, if I run out of battery, then my file system is inconsistent. So I would have nothing pointing to this inode, but in the file system, it would still be marked as used, and it would be kind of lost forever. So you might get in that situation, and you want to be able to recover from it. But in this case, if you don't do anything, it's really, really difficult to recover from it unless you check the entire file system. You walk every name and see, oh, nothing actually points to it, so that inode is actually free. I should probably fix it up, or there's some inconsistency. So that is where journaling file systems come in. So what a journaling file system will do is it will record in the log on a file, like on the physical drive itself. Before it starts doing these 3 steps, it will make sure it writes out what it's about to do. So it will probably write that, hey, I'm about to delete this inode, and then after making sure that that is on the disk, then it would start doing these steps. And if it crashed somewhere in between one of these steps, makes it a lot easier to recover because you would just check the journal. You would see, oh, you started deleting this file and you did not complete it yet. So I need to see if just this is consistent, and I can walk through just that instead of the entire file system and go ahead and clean it up. If, however, you know, the 3 steps actually happen, they're successful, you would just remove that entry from the journal. You have successfully completed it, so you don't need to check it anymore. So, any questions about journaling file systems? So, yep. So if it crashes in the process of journaling, then it would be like you never started deleted the file. So it wouldn't have started anything, so that file, it would just look like you just never accessed the file or you haven't deleted it yet. So it would be at some consistent state before anything happened. Yeah.
Let's say journals, it's going to do step 1.
Sorry?
Let's say journals, it's going to do step 1.
So it just journals like the whole step. So it just says, I'm going to journal, I'm going to delete these 3 things, which implicitly means it's going to follow these 3 steps.
So like, if it journals first and then it removes second, then it can still fail.
So in this case, like deleting a file is these 3 steps. So the journal would just say what it's about to do. So it would write to the journal, I'm going to delete this file, and then before it even did step 1, it would make sure that I'm going to delete this file in the journal.
Like, what if it breaks when it's deleting the file? Or like, it loses power like in the middle of deleting the file?
In the middle of which step?
Deleting the file.
So
I guess like the first step.
So in the middle of doing this? Yeah. So it would just say, okay, well, the journal, it's kind of like a to-do list. So it's like, I'm going to delete this file, right? So it would write that in the journal, and it would be undone. Then it would start trying to remove this directory entry, and maybe it removes the entry, and then power gets lost.
Well, what if power gets lost before it removes it?
Oh, if power gets lost, like it just journals and then power's lost, then, well, the file system would probably still be consistent, but has a pending operation, so it'd probably just do that operation. So if the journal said, I need to delete a file and it's not done yet, that's essentially a to-do list. So as soon as you have power back again, it would check the journal, it would say, oh, I need to delete this file. Oh, I didn't even do step 1. Well, I'll start at step 1 and go all the way to 3 and actually delete it. So you might notice that when you format stuff, especially on Mac OS, it'll be like the file system and then a journal file system, and the default option is a journal file system. So this is what they're talking about when it says journal file system. So it just means your file system will be consistent, but it's also a little bit slower because you have to write to a journal before you do anything. But typically it's fairly fast and it doesn't really matter. All right, any other questions before I guess we work on lab 6? All right, so today we saw even more memory allocations. So the buddy allocator is what most kernels use for most memory allocations. Of course, it can get complicated for other things, but buddy allocator is one of the most commonly used one. It's a real-world restricted implementation, so it only deals with powers of 2 and uses the implementation would use multiple linked lists. And then in the other case, if we know everything is of the same size, then you use the slab allocator. Slab allocators are used all over the place. In fact, it will be used in lab 6 if you haven't started yet, because everything's of the fixed size, so you don't have any fragmentation. So with that, just remember, pulling for you.